Okay, so hello and welcome to lesson number 2 of IP addressing, IPv4 addressing. In this lesson, we look at three things. We talk about network segmentation, and the objective in that part of this lesson is for you to be able to explain how subnetting segments a network to enable better communication. There are some benefits in terms of why we have to segment a network. So we look at those benefits in section 1 of lesson 2, or in topic 1 of lesson 2. And then we look at subnetting an IPv4 network. How are we able to calculate IP version for subnets for a /24 prefix? And this is sometimes known as classful addressing or classful subnetting, where we subnet based on octet boundaries. And then the last section of lesson 2, we look at subnetting a /16 and /8 prefix. Again, calculating IPv4 subnets for the /16 boundary and /8 prefix or /8 boundary. So basically, in those two last two topics of lesson 2, we are looking at subnetting in boundaries based on class C, class B, and class A addresses. See, if you look at /24, that's a class C default subnet mask. /16, when you look at /16, that's the default class B subnet mask. And then we have class A, the private address 10.0 range, 10.0.0.0 range. That's the /8 as the default prefix or subnet mask. Okay, so we'll be looking at borrowing bits within the boundaries of the particular octet we are looking at in that class of address. Okay, so lesson 2 is accompanied with three Cisco videos. As we go through, I'll show you which videos you need to watch, and I'll also upload video links to both our FB group and also on provide the link on NetAcad. Okay, you may also find the video on the reading resources. Okay, so first of all, let's look at network segmentation. And in network segmentation, again, we look at the importance of, or the benefits of, segmenting a network using subnetting. You will notice one of the key reasons here. The first things we will look at is what does broadcast domains have to do with segmentation. Now, by now you should know that routers separate broadcast domains. Remember that routers never forward broadcast. They only every router keeps broadcast within that particular interface where the broadcast originated from. It's never forwarded out to another interface. Whereas when you look at switches are known as devices that separate collision domains. Okay, so switches are related to collision domains. Routers are related to broadcast domains, which means that for a 24-port switch, every single interface on that switch creates a separate collision domain. Unlike a legacy hub device, every interface on a hub belongs to one collision domain, whereas in a switch, every single interface on the switch creates a separate collision domain. For a router, every interface on a router creates a separate broadcast domain. So when we're talking about broadcast domains, again, in terms of a broadcast domain, you can have a router with one interface going to a network, and that network can start off small, and then it will start to grow and grow and grow. And as your network starts to increase in size, the larger your broadcast domain becomes. And there are some problems associated with having very large broadcast domains. So if you see many protocols, they use broadcast or they use multicast. Okay, example is ARP. ARP typically uses broadcast to locate other devices, host, send DHCP, discover broadcast to locate the DHCP server in a particular broadcast domain. And when all these applications, or when all these protocols are used in broadcast, switches propagate this broadcast out to all interfaces except the interface from where it originated from or where it was received. So a switch will receive a broadcast, and it will say, for example, out of all the 24 ports, switch will receive a broadcast from port 1. What it will do is it will forward the broadcast out to all the other interfaces except port 1 from where it received it. So you see, switches propagate broadcasts out all interfaces. In other words, when we have a router, see here router 1, and we have 4 switches. All of these switches will be propagating broadcasts throughout the whole entire network within that interface, G00. The router will never forward the broadcast out to other interfaces. Okay, so routers separate broadcast domain. So each router interface connects to a broadcast domain, and broadcasts are only sent out or propagated within that specific broadcast domain. Okay, so the problem here is that this broadcast can create a lot of unnecessary stress on the network itself, because we want usable traffic to be propagated across the network, not just flood the network with all sorts of broadcasts. Okay, so that's where a bit of segmentation has to be done on a network, and these are some of the problems associated with having large broadcast domains. One problem is the large broadcast domain. This host can generate excessive broadcasts and negatively affect the network, and it's common knowledge, when you have too much broadcast being propagated out to a network, it sometimes can bring the whole network down because it's just too many broadcasts without any usable traffic being sent back and forth. So it can negatively affect the network. And one solution here is to reduce the size of the network to create smaller broadcast domains. And this whole process is known as subnetting. So what we are doing here is we have one interface on a router that creates one broadcast domain. But we can divide that one broadcast domain into smaller broadcast domains by using subnetting. So we are really segmenting the network into smaller groups. Okay, segmenting the network into smaller groups. Sometimes segmenting or subnetting can be done based on different needs in the organization. So you can divide the network address 172.16.0.0, that's a class C, a class B /16, into two subnets of 200 users each, 172.16.0.0/24 and 172.161.0/24. Notice that that's classful. Okay, that's classful addressing. And broadcasts are only propagated within the smaller broadcast domains. How is that broadcast forwarded? Each of those segments will have a broadcast address. So you have the first address, which is a network address. You have the last address, which is a broadcast address. So you don't use first and the last. Whatever is in between, that's what's called your usable address range. Okay, so for example, you have 172.160.0.0/24. Okay, so you will not use 0.0 because 0.0 is your network address. And then your first usable address will be 0.1, 0.2.3.4, all the way up until 0.254. 0.255 will be your broadcast address for that particular segment. And then you have the next segment, 172.161.0/24. So again, 1.0 is your network address. You will not use that. 1.255 will be your broadcast address. You will not use that. So you will use 1.1, 1.2, 1.3, 1.4, 1.5, and upwards. Okay, so those are the addresses you have in between that you're going to use. First address, you don't use that. That's your network address. Last address, you don't use. That's your broadcast. That is why when you look at there are tons of videos on YouTube or other resources that talks about broadcast addresses. If you go through these videos, and if you read about subnetting, you will notice they usually use a formula to find out the number of hosts, and they say 2 raised to the power 2 or 2 raised to the power the number of bits that you're going to borrow to find the host, and then -2. So why they say -2 is you don't use the first address, you don't use the last address, you use what's in between. So the first is your network address, the last is your broadcast address. Okay, so later on we'll look at how we can segment based on the user requirements. Say for example, if we need 400 users, what would be the appropriate class of address or subnet mask, not really class. In this case, if you're using classes to subnet, then you can see here class B will allow us at least up to 400 users, whereas with a class C address, we have less than 200 users, okay, 200 less users that we can for every segment, okay, because of the way the address is designed. The private class C address is designed. Okay, so we've seen some of the problems. Well, one main key problem with large broadcast domains, it can negatively affect or impact the network. That is the reason why we have to segment the network. So several reasons here. If you're going to segment network, when you're subnetting or when you're segmenting using subnetting, you're reducing overall traffic and improving network performance. Okay, that's one key benefit about subnetting. It can be used to implement security policies between subnets. So for example, in some organizations, you have, for example, in Divine Web, we have staff on a separate subnet, we have students on a separate subnet. Okay, so using those subnets, ICT can implement different security policies based on the users within that subnet. Subnetting reduces the number of devices affected by abnormal broadcast traffic. Okay, so this means that you're trying to reduce your network issues. Okay, so if you have if you have a large broadcast domain, whenever you have abnormal broadcast traffic, it affects the whole entire network. Okay, so when you're reducing or when you're segmenting your network into smaller pieces or smaller modules or smaller segments, it's easy to isolate traffic and do troubleshooting or trying to identify issues or diagnose errors within those segments. Okay, so it reduces the number of devices affected by abnormal broadcast traffic. And subnets can be used for a variety of reasons. You can use subnetting based on location. Okay, for example, you may have your POM office one subnet, or within POM you will have different geographical locations. So within Medan or Leh, you will have different geographical locations. Or even within a building, you might have first floor, second floor, third floor, fourth floor, and so on. So you create subnets based on the location, okay, the physical location of the building or physical location of users within the organization. Another reason why you could do subnetting is subnetting based on group of functionality. Okay, sometimes functional departments. Okay, so for example, administration. In this diagram, you have administration in their own subnet, human resource in their own subnet, students in their own subnet, accounting, etc., etc. Okay, so you subnet or you segment users based on their functional departments. Another reason why you could use subnetting is based on device types. Okay, so if you think about the hierarchical network, remember you have the access layer, you have the distribution layer, and then you have the core layer where you have the core devices. You could subnet based on the hierarchical structure, device type, or you could subnet based on the Cisco's modular enterprise modular structure. Okay, later we'll look at that in CCNA 4. So we talk about how you're able to class devices, okay, based on their function or based on the type of device. So there are a variety of reasons here as to why you would segment the network. It depends on a case-by-case basis, how your organization is structured, and what your policy, ICT policy or network design documents dictate how you would set up your network. Okay, the next part of lesson 2 is where we start to look at subnetting an IPv4 network. And the main objective here is to subnet, or not subnet, but calculate an IPv4 subnet for a /24 prefix. Okay, so we are now, when we say /24 prefix, we are now going from class A, B to class C. And remember, there are 5 classes. If you look at the accompanying handout I posted earlier on, if you look at this handout, private address range in IPv4 IPv4 addresses, there are about 5 of them. You have class A, class B, class C, class D, class E. So class A, B, and C are normally classes we typically use in private networks. Okay, we have the class A, the 10.0.0 range, we have the 172.16.0.0 range, and then we have the 192.168 range. Okay, class A, class B, class C. Class D for multicasting, and class E is experimental. Okay, what type of experimental? I'm not sure what type of experimental. Okay, so many resources, articles, books I've read, they don't mention what type of experiments. But lately, there's been a lot of experiments in the area of IoT. So you could find it out. Okay, what type of addresses they're using for experimenting. Okay, most probably in the academic environment or research, science and research environment. Okay, so let's look at calculating an IPv4 subnet based on /24 prefix or class C address, subnet in a class C address. That's basically what it means. Okay, so notice that really what we're doing here is we're subnetting on an octet boundary, okay, depending on what class we are working with. So if you see class A/8, okay, prefix length. By the way, that prefix length it's the same as the subnet mask. Okay, it's just another way of denoting the subnet mask. If you look at the subnet mask 255.0.0.0, remember that there are 4 octets in an IPv4 address. These 4 octets, they are all 32 bits. So one octet is 8, 8, 8, 8, 8, 4 is 32. So when you see 255, that means that all of these bits in that first octet are on. And if you count all those bits, they are 8 bits. So /8. So that's another way of writing your subnet mask, a prefix length. By the way, when you get to IPv6, you will no longer see subnet mask. You will see prefix. You will see prefix /64. You won't be able to see a subnet mask written in that form. In the decimal, denoted in decimal format. Okay, the next class, by the way, class A, notice number of hosts, you have 16 million. 16 million. Now, how did we end up with that number of hosts? Okay, typically when you're trying to find out the number of networks, you read from your left to your right. Okay, if you're trying to find the number of hosts, you start from the right to the left. So notice if you start from, well, if you look at the number of bits that are on, which are 1, there are 8 of them. The rest of the bits are all 0, which represent the host. So if you look at all the bits, you count all of them, that's the number of bits you're going to use. Raise that, 2 raise that to that power, the number of bits for the host. Minus 2 will give you the total number of hosts per subnet. Okay, per subnet. So look at /8, that's quite a lot of host addresses available for you to use. So large, complex, large enterprise networks, this could be a suitable subnet range to use or prefix to use. Look at class B/16. You have the first octet and the second octet, all bits are on. So you are halving the 32-bit IPv4 address right in the center. So you have the first 16 bits for network, the remaining 16 bits for the host. So if you do 2 raised to the power 16, that's how much you end up with, 65,534. Okay, minus 2, of course. 2 raised to the power 16 minus 2, you end up with 65,534 total number of hosts per subnet. Okay, per subnet. When you look at class C/24 indicates that 24 bits are on. They are 1. So you have 255, 255, 255. So now we are working with the last octet. Okay. So if you look at the last octet, how many bits are on? Off. 0. 8. So if you raise 2 to the power 8 minus 2, we end up with 254. So 2 to the power 8, we get 256. So we minus the first and the last one, network address, broadcast address, and we are left with 200 plus, so 254 hosts to be exact, to use in one subnet. Okay, in one subnet. Now, Then by looking at the first class A, class B, class C, when we're talking about subnetting, if you're going to subnet a class A slash 8 prefix, we'll be working with the second octet, third octet, or fourth octet. Okay, that's what we'll be doing. If we're working with the class B address, and if you're going to subnet based on octet boundary, we'll be working with the third octet. Okay, third octet. So class A, we're working with the second octet, meaning we're going to be borrowing host bits from there to reduce the number of hosts within a network and increase the number of networks. Uh, when you look at class C, we'll be working at the last octet, so we'll be borrowing bits from all the 8 zeros here. Okay, see, if you look at class A, it's an inverse relationship, the number of hosts and the number of network. If you look at class A, we have a very high number of hosts, but we have a smaller number of networks. How do we know? If you look at the number of bits that are on 1, there are 8 of them. So 2 raised to the power 8, we have 256 networks. So we can have a total of 256 networks. In each one of those single networks, there'll be about 16 million hosts. Okay, in each of those networks. Okay, and it applies to /16 and /24 as well. Okay, so that's basically an overview of subnetting based on an octet boundary. Okay, so let's look at the first table, 10.0.0.0/8. Okay, is subnetted using /16, and in the second table we have a /24 mask. So if you look at the first table, we have a class A address of 10.0.0.0/8, okay, which is subnetted using /16. So notice when we use /16, we are working now with the third octet. Can you see that? We are now working with the third octet. Okay. We're working with the second octet. Okay. You see we have 10.0, that's the first network, 10.1, second network, 10.2, 10.3, 10.4. Remember that /8, when we are subnetting class A, we are working with the second octet. When we are subnetting a class B, we are working with the third octet. When we are subnetting a class C, we are working with the fourth octet. Okay, so you can see here we have 10.1, 10.0.0.0 is the first subnet. Second subnet will be 10.1.0.0, and then third 10.2.0. So these are all the networks. Okay, these are all the networks, and it goes on until 10.255. Okay, 10.255. That's it. That's where you stop. And notice the broadcast. Okay, so first address is your network address, last address is your broadcast. By the way, when you're subnetting, those are two important things you need to know. There's a video as we go further down. There's a video on the magic number, subnetting with the magic number. Once you know the magic number, you use the magic number, find your subnet address, know your broadcast, and that's it. What's in between your subnet and your broadcast is your usable host range. So if you look at the middle column, these are all the host ranges for each individual subnet within that 10.0.0.0 subnetted using /16. Now look at the second table, subnetted using a /24. Notice now that we are now working with the last octet, okay, rather the third octet. Okay, so we have 10.0.0. Why we have to work with the third octet now is the last octet represents the host. Okay, it represents the host. So we now have 10.0.0.0, 10.0.0.0, that's the first. The second subnet will be 10.0.1, and then we have 10.0.2, 10.0.255, 10.1.0, 10.1.1, 10.1.2. So it goes until we end up with 10.255.255.0. That will be the last subnet. Okay, again we will do this when we do our subnetting activity. I'll do a separate video on that and demonstrate that to you. Okay, have a look at this table here. Now we have 6 ways where you can subnet a /24 network. Okay, so notice the whole idea here is we are playing around with the subnet mask. Okay, we are playing around with the subnet mask. Really, it's a subnet mask that determines how many hosts and how many networks you will have. It's also the subnet mask that gives you an idea of what network you belong to, or any particular IP address belongs to. So if you look at the subnet mask here, notice /24, the last octet now. So if you look at the subnet mask, the first, second, third octets are all fixed. Can you see that? We have 255, 255, 255. You don't touch them. When you're working with subnetting a /24 network, you're looking at the last octet. Okay, so starting from, you have 8 zeros across. Okay, you have 8 zeros across. They are all off. If we borrow 1 bit for the network side, then we have 128. See, that bit value is 128. Remember the 8-bit values: 1, 2, 1, 2, 4, 8, 16, 32, 64, 128. Okay, 8 bits, 128 all the way up to 1. Okay, so if we borrow one of those bits, that bit value is 128. So we will end up with 255, 255, 255 dot 128. Okay, and that's a /25 subnet mask. Okay, it has a prefix of /25, again because of total number of bits for network /25. So the question now is, how many hosts then? So we have how many bits left? 7 bits left. Okay, so if we take that 7 bits, okay, we take that 7 bits, 7 2 to the power 7, we find out, okay, 128, 2 to the power 7, subtract 2, we are left with 126. Now number of subnets is 2. Remember, boundary, okay, boundary line. So this is where we draw, this is where, hold on, this is where our boundary is. Okay, we don't touch this. Okay, we don't touch what's on this side. It's fixed. Okay, so you're only working with this last octet. Okay, that is why when we say the total number of subnets available, only 2. Okay, we could have counted all of this, but we are working with a /24 network. That is why we don't count all of this. We are counting only this 1 bit. So it's 1 bit for the network. So 2 raised to the power 2, okay, is 4. Okay, minus 2, we are left with 2. Okay, again, minus 2, we minus 2 because in legacy networks we don't use the 0 network. Okay, we don't use the 0 network. Sorry, not 2 raised to the power 2, forgive me, 2 raised to the power 1. Okay, okay, so we end up with 2 again. So that's a total number of subnets. /26, again we have a total 24 here. We borrow 2 bits, 1 2. Okay, and then we have 1 2 3 4 5 6. Okay, 2 to the power 6 minus 2, we end up with total of 62 hosts. Okay, 2 bits, 2 raised to the power 2, 4. Okay, so we have 4 subnets, and it goes on until we reach this. Okay, we go to /30. If we go /31, 32, that will be the end of it. 32, that's not a subnet. Okay, that's a unicast address. /31, that will not leave you enough IP address to work with. Okay, so that's basically subnetting within the /24 octet boundary. Okay, the key idea here is we are working with octet boundary. So when we know that it's a /24, we draw our line at the 3rd octet, and we now work with the last octet. Okay, we don't touch the 1st, 2nd, 3rd octets. We don't touch them. Okay, so let's have a look at the next one. Try to watch this video. The purpose of the subnet mask, the video will demonstrate the process of subnetting. So you can find a video in the course resources, or check out the FB group. there's also another video on subnetting with the magic number. Okay, so I'll also explain this in a separate video as well. Okay, the last part of lesson 2 is subnetting a /16 and a /8 prefix, and same concept here. Remember, the key idea here is for us to find the boundary. Okay, for us to find the boundary. So notice, if we're creating subnets with a /16 prefix, we are now working, it's a /16, remember, we don't touch half of the octets. Okay, so we draw a line there, we don't touch everything that's on this side. Okay, we don't touch that. So we are now working with the third octet and the fourth octet. Okay, so when you look at this, you see we start borrowing bits from here, we go here, we go, and we keep borrowing bits until we have used up all the bits of the third and fourth octets. Okay, similar concept here. Now, question that you should ask here is, why are we borrowing bits from left to right? Remember what I said earlier on? We're borrowing bits from left to right because we want to increase or decrease. Okay, especially when we're borrowing bits, we want to increase the number of subnets. Okay, so notice, if you're creating subnets with a /16 prefix, you start borrowing bits from the not just the /16, /8, /24. You start borrowing bits from the left to your right. So you see, it starts from the left and it starts borrowing bits to the right until all the bits are all used up. Okay, that's the whole idea here. If you want to find out the number of hosts for any particular prefix, you're either working with /24 or /16 or /8, it's the opposite. You borrow bits from the right, making your way to the left. So again, notice the inverse relationship between the number of subnets and the number of hosts. As the number of subnets increases, notice what happens. The number of hosts decreases. Okay, as the number of subnets increases, the number of hosts decreases. So it's an inverse relationship between the number of subnets and the number of hosts. So have a look at the next example here. If you're creating 100 subnets with a /16 prefix, then you have to ask yourself, how many bits do I borrow starting from the third octet onwards? How many bits do I borrow that will give me 100? Okay, 100 subnets. Okay, so just, you can pause this video for a while. I normally put an X. Okay, I usually do this. I put X, I write it here, X dot, okay, and then dash dot dash. What this means is that I don't touch the first two octets. Remember, it's a /16 prefix, so we don't touch the first two. So we will start borrowing bits from this octet going that way. Okay, so if we borrow 1 bit, that's not enough. 2 bits, it's not enough. 3 bits, it's not enough. Remember, 2 raised to the power 3 is 8. Okay, still we need 100. So to cut this short, think about the number of bits. 4, 5, 6. We know that 2 raised to the power 7 gives me 128. Okay, so 128 is enough. If I go 2 to the power 6, that will be less than that. So 2 to the power 7, 128 subnets. I only need 100 subnets. The 28 can be extra subnets that can be there. So that means I'm now going to borrow 7 bits. So we start borrowing bits from this third octet onwards. So we go 1, 2, 3, 4, 5, 6, 7. And then the last bit will be a 0. And then the rest of this will be all 0, all 8 of them. Okay. So 7 bits were borrowed for the host, okay, for the network, sorry. 7 bits were borrowed for the network. And then how many bits left for the host? So we have 8 bits plus 1. We have 9 bits for the host, okay. So this should give you the total number of subnets. This should give you 2 raised to the power 9 minus 2 should give you the total number of hosts in each of those subnets available. 2 raised to the power 7 will give you 128. So in each of those 128 subnets, we should have 2 raised to the power 9 minus 2 hosts within each of them. Okay, I believe this is all, you getting a hang of this by now. Okay, so we are working with the boundaries. Okay, we are working with the boundaries. The last example, creating 1000 subnets with a /8 prefix. Again, same idea here. You start borrowing from the left, making your way across to the right, and then you see how many bits. 2 raised to what number of bits will give you at least 1000 subnets, not less, and not exactly 1000, but at least 1000. It could be extra. Okay, so example here, 2 raised to the power 10, 1024 subnets. So that's enough. So you will use 1000, 24 will be extra subnets. In case the network expands, you can have the extra 24 subnets to be used. Okay. Okay, so in this lesson, what we covered was basically, we talked about subnetting using /16 prefix, /24 prefix, /8 prefix, and when we are subnetting based on prefix boundaries or subnet boundaries, we look at the default classes. So class A/8, we don't touch the first 8 octets. Class B/16, we don't touch those 2 octets, the first and the second octet. /24, we don't touch the first 3 octets. We work with the last octet and we borrow bits from there to find out the number of subnets we can have in that class of address, and we also find the number of hosts in that class of address. Okay, so have a look at this video. That's video number 3, subnetting across, video number 4, subnetting across multiple octets. That video will demonstrate that to you. Okay, so what I'll do is in a separate video, I'll try to give an example, work out an example on basic subnetting. Later we'll look at, in lesson number 3, we'll talk about variable length subnet mask. This is where we now go classless. Okay, notice everything we've talked about in this lesson, we've been talking about classful, classful, classful. We are working with a class of addresses and subnetting based on the boundaries of the prefixes. In variable length subnet masking, VLSM, this is where you now disregard the classes. You don't talk about fixed number. This is variable length. Okay, you're now working with classless. Okay, sometimes you will notice they refer to this as CIDR, CIDR, classless interdomain routing. That's /24, /27/28. They will not refer to it as prefix. Some material you will notice they call it CIDR. Okay, CIDR, CIDR is short for classless interdomain routing. Okay, so that brings me to the end of lesson number 2.